Bismillah ar-Rahman ar-Rahim. This is a continuation of the previous video on disinfection slides. This is an example to check the application of Check's law. So we have the data in the first three columns. These should be given. Okay, and this is the concentration of the disinfectant. Here, they want to graph the data for the inactivation of the polyvirus type 1. So we are inactivating polyvirus type 1. Using what? Using the disinfectant bromine. And he wants to determine the Check's law rate of constant for each of the two disinfectant concentration. So we have, first of all, you're adding bromine at 21.6 milligram per liter. And they are checking this versus bromine at 4.7 milligram per liter. Two experiment. And they are checking the time from 0 to 2 seconds for the concentration 21.6 milligram per liter bromine. And they are checking how much, what is the number of organisms, number of polyvirus type 1 reduction from 500 number of polyvirus type 1 to 40, to 3, to finally to 1, and then to 0.2. This is the number of the polyvirus type 1 reduction from 500 to 0.2. Also for the next concentration of bromine, the 4.7, the time goes from 0 to 4 seconds. We give extra time here. And you can see that the number, we make sure that it has initially the same number of polyvirus type 1, 500 all the way to 1.5. Okay. Now, we need to plot it and find out the constant K to see which one of them is more effective. Now, let's do N over N naught. Remember the equation? The equation N over L naught. So this is, ln, let's see, NT over L naught minus KT. So, of course, here there is no zero. There is no intercept and should not be close to the 0, 0. So this is y-axis. Remember the equation from calculus 1. This is the y-axis, and this is the x-axis, and this is the slope. The slope going to be k. Of course, it's going to be going down, and that's the meaning of a minus. And b is, there is no intercept with a 0, 0. So that's why we need to find out nt over L naught. So, you can see what is NT. Initially, it's 500. And what is the final one? Still 500. So 500 over 500. This is NT, 40. What is L naught? 500. So this is 40 over 500. Next, 3 over 500. L naught will not change. The initial number will not change. The only thing that will change is NT. And this is 1 over 500. And this is 0.2 over 500. Same thing you do it here. For the next concentration of bromine, 500 over 500. Because NT and L naught is the same. This is 79 over 500, 25 over 500, 3 over 500, 1.5 over 500. And now it's either you do log or len, but here you're going to do the log, N over N naught. So the log of this, log 1 is 0, log 0.08 is minus 1.1, minus 2.2, minus 2.7, minus 3.4. And now we will plot the log n, or the len n over nt over L naught versus the time you have here. This is the time for each one of them to check which one of them is highly effective. So once you plot the log n over L naught versus the time in seconds, you can see that the C 4.7 has a best fit like this. And of course, the other one, the 21.6, has a line like this. The best fit is like this. And of course, here, if you could ask Excel to give you the best fit with the equation y is equal minus 0.6667x and r squared is 0.9792. Same thing for the other equation, minus 1.833x, r squared is 0.96. This is a very nice fit. This is K, and this is K. Don't worry about the minus, it is going down, it's decreasing. So right now, so the value of the slope corresponds to the check low rate constant. Let's see, for the disinfectant concentration, which is the bromide concentration of 21.6 milligram per liter, K is equal, we could call it K base 10 or K base len. K base 10 is 1.8333 per second. And the other concentration of the bromine, 4.7 milligram per liter, the K base 10 is 0.6667 per second. Of course, in the book, he also found the len, the base E. So you can see that either with the base E, the 1.54 second for the 4.7 milligram, and 4.22 per second for the 21.6 milligram, it's also indicate the same thing. It also indicate that the Besedo first order rate constant, K, you can see it is increasing with the 21.6. So when you add more bromine, you will have high inactivation. Okay? Don't worry about the minus. The minus means it's going down. But we can see that once we add more bromine, we have high inactivation of polyvirus type 1. Also, sometimes in disinfections we use CT approach, or the product concentration versus time, this times T. This could be also viewed as dosage of disinfection, because always we care about the time that the chemical is in contact with the disinfecting agent. So C is the concentration of the chemical disinfectant in milligram per liter. And this is measured after the time segment, after the time it contacted with that disinfectant agent. T is the time required to achieve a level of inactivation. Sometimes for ultraviolet, there is another similar concepts of UV, it's I, milliwatt per centimeter square, and the time of exposure, time T. And we could call it, for UV, we could call it IT. I times T, I in unit of milliwatt per centimeter square per second, or millijoule per centimeter square. This is used only for UV disinfection to compute the dosage, how much UV light is needed. The CT approach is a very useful one because it compares the relative effectiveness of different disinfectants and the resistance of different organisms. Not all the organisms are not going to resist. Some organisms will resist the disinfectant agent. So the CT approach is very useful to check relative effectiveness of different disinfectants and also the resistance of different organisms. In the next figure, we'll illustrate comparing the CT and IT required for 99% inactivation of several microorganisms using the 5 common disinfectants. In this figure, it shows that you could see it right now. Ozone requires lower CT for most microorganisms than the other 3 chemical oxidants. Now, you can see it from this next figure. So, next figure, let's look at the ozone. This is the CT. You can see the CT, it goes from 0.01 to 10,000. You can see ozone required lower CT than the rest of the common disinfectant agent, chloramine, free chlorine, chlorine dioxide, and UV light. Okay, so ozone required less C times T. This is good, very effective. Okay, the meaning of that, it is a very stronger disinfectant, ozone, of course. Also, we could look at C. barium. Barium, the microorganism C. barium requires highest CT. Among all the chemicals, oxidants, which mean that this microorganism is most resistant to these disinfectants. Let's look at C. barium. Okay. Look at this. C. barium and chloramine need the highest CT. C. barium and free chlorine, they need the highest in CT for free chlorine. And look at this C. barium, and then and here it's still the same thing. It's always at the top of the list. Okay, for the UV light, we don't see it, but we could see from the other disinfectant that C. barium is very resistant to chloramine, free chlorine, chlorine dioxide, and ozone. That's why they are in the top list of CT. Okay, so another conclusion of this graph, it could be found to the right, that the requirement for 99% inactivation. This chart compares the CT or IT for the UV light and CT for the rest. Required for 99 activations of the several pathogens using 5 common disinfectants. Ozone required, this is the very nice conclusion, a lower CT for most pathogens than the other 3 chemical oxidants. And also the microorganism C. barium requires highest CT among the 4 chemical oxidants. So this microorganism is most resistant to these disinfectants. Nice graph. So we will define CT one more time. CT product, or C times T, is a combined effect of disinfectant concentration and time of contact to achieve certain level of inactivations for a given microorganisms. It can also be viewed as dosage of disinfectant. In addition to C and T, what factors influence the rate of chemical disinfection? Of course, this will affect rate of chemical disinfection, but other factors than C and T, the other main factors that influence the rate of chemical disinfection are pH and temperature. Remember the pH example we had previously at the first few chapters. And also, what kind of microorganisms is most readily inactivated by free chlorine? Because we use chlorination a lot. Of course, adenovirus, calivirus are most readily inactivated by free chlorine. And also, the next question, what kind is most difficult to inactivate? Of course, C. barium, you saw it from the graph before, is the most difficult to inactivate. You have to add more of that disinfectant chemical. Let's look at this application of CT. Surface water treatment requires that at least 99.99%. 99.99% inactivation mean 1, 2, 3, 4. 4, we call it 4 log removal. So 99.9, that's 3 log removal. This is one way of the abbreviation we use a lot. So 4 log mean 99.99. And or inactivation of viruses, a water treatment plant provides disinfectant using free chlorine with a contact time of 30 minutes. Contact time means meeting time. The chlorine disinfectant and the water with the pathogens. Now we are doing viruses removal. Determine the concentration of the free chlorine. He wants to know the concentration of the free chlorine for disinfection at pH 7. Water temperature is 5 and 20. CT values are provided. CT is 8 milligram per liter at pH 7. And at 5 Celsius, CT is 3 minutes per milligram per liter at pH 7 and temperature 20 Celsius. Now, the required residual concentration of the free chlorine for the given contact time of 30 minutes, that we're going to do the first of all the 30 minutes, is determined as follows. Okay, remember it was CT, 30 minutes. What was the CT initially? The CT for the 30 minutes, it was, what is it, 3 minutes, so we're going to use this one, CT, pH, and 20 Celsius. And we're going to use the other one later on. So we have 8 minutes, and we have CT, 3 minutes. Let's look for the 8 minutes milligram per liter. What was the time? The time here that we're going to be using is 30 minutes. So we find the concentration by dividing 8 milligram per liter over 30 minutes. And that's what gives you 0.27 milligram per liter of the disinfectant agent that they're going to be using, chlorine here, free chlorine. And the next one is concentration is equal 3 over 30 minutes, and that's 0.1 milligram per liter. Remember, in one of them, he used here 5 Celsius is for the CT of 8 minutes, and 20 Celsius, he used it for the CT 3 minutes. So we put C20 and C5. Look at this lower temperature. The higher the CT values are required. So the lowest the temperature, there is a need for a higher CT values. Therefore, a higher concentration of free chlorine may have to be applied during winter months, which means that you're going to spend more money during the winter season. Okay? You're going to add more free chlorine. While this is still not summer, 20 is almost spring or late winter, it's 0.1, you're going to add less. Okay? There is many agents that going to be used for at the household levels in developing world. Let's say if you have water and you suspect that this water has disinfectant, you could apply heat, which is boiling. This is the most important mean of treating water in the developing world, but requires valuable wood in the developing world, of course, that produce air pollution and has safety concerns related to scalding of children, because water has a flat and deaerated taste. And most experts suggest attaining a rolling boil for 1 to 5 minutes. The WHO recommends reaching a rolling boil. This gets you an excess of temperature and needed for sterilization. Heating to do a pasteurization temperature of 60 Celsius for 1 to 10 minutes will destroy many waterborne pathogens. So this is the guidelines for heating. Sometimes they use solar. This could take time and work with limited volumes of water. Of course, using combination of UV, ultraviolet, and pasteurization processes for disinfections, heating to pasteurization temperature 6 Celsius for 1 to 10 minutes will destroy many waterborne pathogens. Of course, solar disinfection is a very simple treatment method that takes advantage of the bacterial destruction potential of sunlight. Treatment involves placing clear bottles, of course it has to be clear, of water to be treated in direct sunlight for a determined amount of time. Remember C times T or I times T, radiation from the sun, and the radiation from the sun times the time of contact. Sometimes you will have solar cookers or reflectors made of cardboard or aluminum foil to reflect the sun back to that bottle. Can attain pasteurization temperatures of 65, which is really good. Chlorination is in the other time you could add bleach. By itself, impart taste to water, requires turbidity to be below 1 to 5 NTU. The WHO guidelines for chlorine is 5 milligram per liter, which is above the taste threshold of 0.6 to 1 milligram per liter. Of course, liquid laundry bleach is readily available source of chlorine in many developing communities. The powder form of chlorine is calcium hypochlorite, which include chlorinated lime, tropical bleach, bleaching powder, and HGH. Calcium hypochlorite can be found in 30 to 70% solution. Liquid bleach is in the form of sodium hypochlorite, contains 1 to 18% chlorine. It's still very good. Still very good disinfectant agent. At the community level, chlorination pots are added to hand dug wells and use bleaching powder or chlorinated lime. Pressed calcium hypochlorite tablets, can also be added to hand dug wells. You could add some tablets as chlorination will start working after you add it. Mechanical chlorinators with no moving parts are sometimes constructed on top of the water storage tank, and a drip of bleach solution into the tank. At the household level of 1% chlorine stock solution can be used. Chlorine is added at 1 to 5 milligram per liter to achieve residual of 0.2 to 0.5 milligram per liter after contact time of 30 minutes. This increased to 1 hour contact time for cold waters. Remember, the cold waters, it needs more disinfectant. Iodine is the other one, which impart taste to water. The WHO recommends a dosage of 2 milligram per liter of iodine with a contact time of 30 minutes. Iodine is better at penetrating particulate matter. Some particulate matter will hide some pathogens within. So this is good that iodine will penetrate these particulate matter better than chlorine, but of course it's more expensive. Sedimentation and filtration is one other way. The 3-pot system used a series of 3 pots where water is transferred between pots daily, and gravity settling reduces helminth, ova, and this is the eggs, and some protozoa by more than 90%, especially with 1 to 2 days storage. Of course, viruses and bacteria removal are much smaller because the density size is very smaller. Filtration can consist of a wide variety of media: granule media, slow sand filter, fabric paper, canvas, and ceramic, and can be also good to remove the pathogens. Okay, let me just see now. The effectiveness of regularity limits and chemical source of the 5 most common. This table also shows the effectiveness of bacteria, viruses, protozoa, and endospores. Free chlorine, effective in inactivating bacteria and viruses. And of course, protozoa, fair to poor, and endospores, poor to good. So let's go ahead and look at the excellent. And of course, you could look whatever you have availability in work, you could use whatever you want. But free chlorine is excellent in removing bacteria and viruses. Monochloramine is not that good, or good to fair to poor. Chlorine dioxide is excellent in removing bacteria and viruses. Ozone, bacteria and viruses, excellent in activating them, and endospores. So ozone is not good with protozoa. Or it's also good, but we are looking only for the excellent. UV light is excellent to inactivate protozoa. Also good for bacteria, and fair for viruses, and fair for endospores. Of course, this is the most common now, and this is the very common, and this is increasingly now coming to be common. Regular limit on residual. You remember the residual that we were talking about in the last lecture? 4 milligram per liter extra free chlorine, 4 milligram per liter monochloramine, 0.8 milligram per liter carbon dioxide, and here there is no residual, because this is, you're talking about radiation. You're adding ozone gas, and you're adding light. You don't expect that this will stay in water. So only the chemicals will stay in water. So the residual only from these chemicals. Now, there is a problem here, that there is a formation of chemical byproduct. You're adding a disinfectant, and there's something bad is being created. Yes, it's killing the pathogens, but it's also creating a byproduct, a harmful byproduct. Let's look at the regulated byproducts. Free chlorine will form 5-trihalomethane, THMs, and 4-haloacetic acid, HAAS. That's not good. Monochloramine will traces of THM. THM right now is trihalomethane, and HAAS is haloacetic acid. Here in chlorine dioxide will produce chloride. Here ozone will produce bromate. UV does not produce anything. Byproducts that may be regulated in the future, several, one of them. Here we will thinking of monochloramine, cyanogum halide, and NDMA. Chlorate is also will be regulated in the future, and biodegradable organic carbon in ozone, and still nothing known for UV light to produce, even for the future. Typical application dosage for free chlorine is 1 to 6 milligram per liter, 2 to 6 milligram per liter for monochloramine, 0.2 to 1.5 milligram per liter for chlorine dioxide, 1 to 5 milligram per liter for ozone. For the UV light, 20 to 100 millijoule per centimeter square. This is the typical dosage. Now, the chemical source or delivered as for free chlorine is either liquid gas in tank cars, 1 ton and 68 kilogram cylinders as calcium hypochlorite powder for very small application, or inside generation from salt and water using electrolysis. Same thing for monochloramine. Same source as for chlorine. Ammonia is delivered as aqua ammonia solution, liquid gas in cylinders, or as solid ammonium sulfate. Here, monochloramine, because there is an amine, there's ammonia here. Chlorine and ammonia are mixed in treatment process to produce the monochloramine. How could you create chlorine dioxide? Same source as chlorine, but chloride as powder or stabilized liquid solution. ClO2 is manufactured with an on-site generator. Ozone, the source is manufactured on-site using a corona discharge in very dry air or pure oxygen. Oxygen is usually delivered as a liquid. Oxygen is also manufactured on-site in some very large plants. UV light uses low pressure high intensity UV 254 nanometer or medium pressure UV several wavelength lamps inside the tank or inside the contactor of disinfection. Now let's look at the tank or the contactors for each one of them. For the free chlorine, in the past was added at the beginning of the plant and residual carried through. Increasingly, individual contactors are used. For the monochloramine, in the past was added at beginning of the plant and residual carried through it, and increasingly individual contactors are used. Also, chlorine dioxide in the past was added at the beginning of the plant and residual carried through. Increasing individual contactors are used. Ozone has always been added, and especially engineered contactors. These contactors are using more compartments. Contactors with more compartments. You will see it in a few seconds. The UV lights, lamps, are placed in gravity channels or in specially manufactured UV reactors because the contactor or the contact time is so short. Reactors must be tested. Oops. Okay, we'll be talking about membrane in the next lecture.